Light hits a mirror and bounces back. Simple enough. Ask anyone to explain what happens, and they'll tell you that light travels in straight lines until it encounters a reflective surface, then follows the law of reflection. Angle of incidence equals angle of reflection. This explanation works perfectly for building telescopes, designing camera lenses, and understanding rainbows. It's taught in every physics textbook, demonstrated in countless classrooms, and seems to capture everything important about how light behaves. But this explanation is completely wrong. The real story of what light does when it encounters a mirror is so strange, so fundamentally different from our everyday intuitions, that even the physicist who discovered it admitted he couldn't truly explain why nature works this way. The physicist was Richard Feynman, and what he found challenges everything we think we know about the nature of reality itself. Feynman's discovery emerged from his attempt to understand the most basic interaction in the universe: what happens when light meets matter? This might seem like a settled question. After all, humans have been observing light bouncing off surfaces for millennia. But when Feynman applied the principles of quantum mechanics to this seemingly simple process, he uncovered a mystery that remains unsolved to this day. The mystery begins with a simple observation. When light reflects off a mirror, we assume it bounces from the point where it hits the surface. But Feynman realized that if you apply quantum mechanics consistently, this picture becomes impossible to maintain. Light doesn't reflect from a single point on the mirror, it reflects from every point on the mirror simultaneously. Think about what this means. When a beam of light approaches a mirror, every single point on that mirror's surface participates in the reflection, even points that seem completely irrelevant to the light's path. The light coming toward the center of the mirror somehow knows about every inch of the mirror's surface, from the very center to the edges and corners. The entire mirror participates in creating the reflection, not just the spot where common sense says the light should bounce. This discovery emerged from Feynman's attempts to reconcile quantum mechanics with the classical theory of light and electromagnetism. Classical physics treats light as waves that propagate through space according to well-defined mathematical rules. Quantum mechanics treats light as particles called photons that somehow exhibit wave-like behavior under certain circumstances. The challenge was to create a single, consistent theory that could explain both the wave and particle aspects of light. The theory Feynman developed, called quantum electrodynamics, or QED, provides the most accurate description of light-matter interactions ever achieved. Its predictions match experimental measurements to more than 10 decimal places, an accuracy comparable to measuring the distance from New York to Los Angeles to within the width of a human hair. But the price of this accuracy is accepting a picture of reality that defies every intuitive notion of how things work. In Feynman's formulation, light doesn't travel from one place to another along a single path. Instead, it travels along every possible path simultaneously. When light goes from a source to your eye via reflection from a mirror, it doesn't just take the path that follows the law of reflection. It also takes the path that bounces off the very edge of the mirror, and the path that somehow travels backward in time before bouncing forward, and paths that loop around in spirals, and paths that venture off to distant galaxies before returning to complete the reflection. All of these paths, every conceivable route light could take from source to destination, contribute to what you observe. The light you see represents the sum total of all possible paths, weighted according to quantum mechanical principles that determine how much each path contributes to the final result. Most of these paths cancel each other out. The spiraling paths, the time-reversed paths, the paths that detour through distant regions of space. Their contributions to the final result are typically so small and interfere so destructively with each other that they produce no observable effect. But they are mathematically real components of the light's journey, and under certain circumstances, their effects can be detected and measured. The paths that survive the cancellation process are those that lie close to the classical path predicted by the law of reflection. These paths reinforce each other rather than canceling out, which is why light appears to follow a single, well-defined trajectory in everyday experience. But this single trajectory is not fundamental. It's an emergent property that arises from the interference between an infinite number of more fundamental quantum paths. This reveals something profound about the nature of light itself. Light doesn't decide where to go based on local conditions at each point along its path. Light somehow evaluates all possible destinations simultaneously and chooses its behavior based on global information about the entire system. When light reflects from a mirror, the behavior of each photon depends not just on the local properties of the mirror at the reflection point, but on the shape, size, and orientation of the entire mirror. You can demonstrate this directly with a simple experiment. Take a mirror and carefully cover portions of it with opaque material, leaving only small strips of reflective surface exposed. If light only bounced from individual points, covering distant parts of the mirror should have no effect on reflections from the uncovered areas. But that's not what happens. Blocking portions of the mirror changes the nature of the reflection from the remaining exposed areas, even when the blocked and unblocked regions are far apart. The implications extend far beyond mirrors. Every interaction between light and matter exhibits this same non-local character. When light passes through a lens, every part of the lens contributes to focusing the light, not just the regions that the light ray diagrams suggest are important. When light creates colors in a soap bubble, the iridescent patterns depend on the thickness of the soap film across its entire surface, not just at isolated points. This non-local behavior becomes even stranger when you consider what it implies about the nature of information in quantum systems. For light to know about the entire mirror when it reflects, information about the mirror's complete configuration must somehow be available at every point where reflection occurs. The quantum fields that describe light and matter must carry information about the global properties of systems, not just local conditions. But how can this information be transmitted and processed? Classical physics allows information to travel from place to place, but only at finite speeds and through continuous paths. Quantum mechanics seems to require instantaneous access to global information, which appears to violate the fundamental principle that nothing can travel faster than light. The resolution of this apparent paradox leads to one of quantum mechanics' most mysterious features, entanglement. When light interacts with a mirror, the quantum states of the light and the mirror become entangled, meaning their properties remain correlated regardless of how far apart they might be. This entanglement allows the light to respond to changes in the mirror's configuration instantaneously without requiring any signal to travel between them. But entanglement itself raises deeper questions. What mechanism maintains the correlations between entangled systems? How does changing one component of an entangled system instantly affect distant components? Feynman himself acknowledged that these questions have no satisfactory answers within current physical theory. Quantum mechanics provides precise mathematical tools for calculating the results of entanglement, but offers no insight into why entanglement exists or how it works. The mystery deepens when you consider the role of measurement in quantum systems. According to standard quantum theory, light exists in a superposition of all possible paths until the moment it gets detected. The act of measurement somehow forces the light to choose specific paths from the infinite range of possibilities. But this description raises more questions than it answers. What constitutes a measurement? How does the measurement process select specific outcomes from quantum superpositions? Why does measurement seem to occur at particular moments rather than continuously? Different interpretations of quantum mechanics provide different answers to these questions, but none of the answers is fully satisfactory, and many physicists believe the measurement problem represents a fundamental gap in our understanding of quantum reality. Feynman's approach to these questions was characteristically pragmatic. Rather than trying to explain why quantum mechanics works the way it does, he focused on developing mathematical tools that could predict the results of experiments with unprecedented accuracy. His sum over paths formulation provides a recipe for calculating quantum amplitudes by considering all possible ways a quantum process can occur, but it offers no insight into why nature should be organized this way. This pragmatic approach led to remarkable technological advances. Quantum electrodynamics enabled the development of lasers, LEDs, solar cells, and countless other devices that depend on precise understanding of light-matter interactions. The theory's predictions have been confirmed in thousands of experiments across many decades. By any practical measure, Feynman's theory of light is one of the most successful achievements in the history of science. Yet the theory's success makes its conceptual mysteries even more puzzling. How can a theory that we don't really understand work so incredibly well? How can mathematical formalism that seems to contradict basic notions of locality and causality provide such accurate predictions about the behavior of real physical systems? Part of the answer lies in recognizing that Feynman's theory describes correlations between measurements rather than describing the intrinsic properties of light and matter. The theory tells you what you will observe when you perform specific experiments, but it doesn't tell you what light really is independent of observation. This shift in emphasis from describing reality to predicting observations represents a fundamental change in how physics approaches the question of understanding nature. But this shift also highlights the limitations of current physical theory. If physics can only predict what we observe rather than explaining why we observe it, then crucial aspects of reality remain beyond scientific reach. The success of quantum electrodynamics in making predictions doesn't resolve the deeper question of why the universe is organized to make those predictions possible. Consider what happens when you look at yourself in a mirror. The light that creates your reflection has somehow sampled every point on the mirror's surface. Each photon that reaches your eye carries information about the global configuration of the mirror, information that was collected through processes that quantum theory can describe mathematically but not explain conceptually. The photons don't start with this global information. They acquire it through the interaction process itself. But the mechanism by which local interactions can generate global knowledge remains mysterious. It's as if the universe possesses some kind of distributed intelligence that allows local processes to access information about distant regions of space and time. This suggests that the space between objects might not be empty in the way classical physics assumed. If quantum processes require access to global information, then space itself might be structured in ways that facilitate information storage and transmission. The quantum vacuum might be not a passive background against which events occur, but an active medium that participates in the fundamental processes that govern physical reality. Some physicists speculate that quantum entanglement represents evidence for this kind of active structure in space itself. The correlations between entangled systems might be maintained by features of space-time that exist below the level of classical physics. These subquantum structures would be responsible for the non-local aspects of quantum mechanics while remaining invisible to current experimental techniques. But such speculations remain highly controversial among physicists. The majority of physicists prefer to focus on the practical applications of quantum theory rather than trying to resolve its conceptual puzzles. This pragmatic approach has been extraordinarily successful, leading to the development of revolutionary technologies that depend crucially on quantum mechanical principles. However, the conceptual puzzles refuse to go away. They become especially acute when you try to understand how consciousness fits into the quantum mechanical picture of reality. Human observers play a crucial role in quantum theory. Measurements performed by conscious observers seem to be what forces quantum systems to choose specific outcomes from their range of possibilities. But consciousness itself remains scientifically mysterious. We don't understand how neural processes give rise to subjective experience, and we don't understand how subjective experience might influence physical processes. The fact that consciousness seems to play a fundamental role in quantum mechanics suggests that the hard problems of consciousness and quantum mechanics might be closely related. Feynman himself was skeptical of attempts to connect quantum mechanics with consciousness. He argued that the mysteries of quantum theory should be addressed through better experiments and mathematical formalism, not through philosophical speculation about the nature of mind. But the connection between observation and quantum measurement seems to require some kind of interface between physical and mental phenomena. This interface becomes particularly puzzling when you consider delayed choice experiments, in which decisions made by conscious observers seem to retroactively influence the behavior of quantum systems. These experiments suggest that conscious decisions can affect physical events that occurred before the decisions were made, which appears to violate basic assumptions about the relationship between cause and effect. The implications extend beyond physics into questions about free will and the nature of time itself. If conscious decisions can influence past events, then the future might influence the past in ways that make the usual notion of temporal sequence meaningless. The universe might be organized as a unified whole in which past, present, and future are equally real and mutually interdependent. These speculations push well beyond the boundaries of current scientific knowledge. They represent attempts to grapple with the conceptual implications of quantum mechanics, rather than simply accepting its mathematical formalism as a tool for making predictions. Most physicists regard such speculations as premature. We need to understand quantum mechanics much better before we can hope to understand its relationship to consciousness and time. But the speculations highlight the depth of the mysteries that Feynman uncovered. His theory of light revealed that even the most basic physical processes involve aspects of reality that resist explanation in familiar terms. Light doesn't behave like particles moving through space, and it doesn't behave like waves propagating through a medium. It behaves like something for which we have no adequate conceptual model. The mathematical formalism works perfectly. It predicts the results of experiments with extraordinary accuracy. It enables the design of technologies that depend on quantum mechanical principles. But it doesn't explain why light behaves the way it does, or why the universe is organized in ways that make such behavior possible. This gap between mathematical description and conceptual understanding represents one of the deepest unsolved problems in contemporary science. We have incredibly powerful tools for predicting and manipulating quantum systems, but we lack satisfying explanations for why those tools work. The universe remains fundamentally mysterious, despite centuries of scientific progress. Feynman's response to this situation was characteristic. Nobody understands quantum mechanics. He meant this not as an admission of defeat, but as recognition that understanding might require abandoning many of our basic assumptions about the nature of reality. The universe might be stranger than we imagine, or even stranger than we can imagine. Yet this strangeness shouldn't be seen as a limitation of human knowledge. It might reflect fundamental features of reality itself. The universe might be organized in ways that resist complete conceptual understanding while remaining mathematically tractable. The mystery might be not a problem to be solved, but an essential feature of what it means for anything to exist at all. From this perspective, Feynman's discoveries about light represent not just advances in physical theory, but insights into the deepest structures of reality. They reveal that the universe operates according to principles that transcend familiar notions of space, time, causality, and locality. Understanding light requires accepting that reality itself might be far stranger and more wonderful than our everyday experience suggests. These phenomena all share the same mysterious feature that troubled Feynman. They require light to have access to global information about experimental configurations that shouldn't be available to individual photons following local paths. The light behaves as if it can survey the entire experimental setup instantaneously and adjust its behavior to match the global constraints. Even the most mundane optical effects exhibit this mystery. When light refracts at the boundary between two materials, the bending follows Snell's law with extraordinary precision. But Feynman showed that this precise behavior emerges from the interference between an infinite number of quantum paths, most of which violate Snell's law dramatically. The light doesn't follow Snell's law because it knows about the law. Instead, Snell's law describes the statistical outcome when all possible paths interfere quantum mechanically. The law emerges from the interference pattern, not the other way around. This reverses our usual understanding of how physical laws work. Rather than determining how things behave, laws describe the patterns that emerge from more fundamental quantum processes. Why does light behave as if it explores all possible paths simultaneously? How does quantum interference select specific outcomes from infinite possibilities? What mechanism enables the instantaneous correlations observed in entangled systems? How does measurement collapse quantum superpositions into definite states? These questions define the current frontier of fundamental physics, yet they remain as mysterious today as they were when Feynman first formulated them. The mathematical formalism that Feynman developed provides extraordinary predictive power, enabling technologies from lasers to quantum computers. But this practical success only makes the conceptual mysteries more profound. We have learned to manipulate light with unprecedented precision while remaining fundamentally ignorant about what light actually is. The light reflecting from your mirror right now exhibits all of these mysterious properties. Every photon that reaches your eyes has sampled the entire mirror surface through processes that remain fundamentally inexplicable. The reflection you see represents the outcome of quantum processes that involve every possible path light could take, weighted according to principles that work perfectly in practice but resist conceptual understanding in every fundamental way. This is what Feynman discovered about light that no one can explain. Light behaves as if the entire universe is present at every point, as if information travels instantaneously across arbitrary distances, as if the future influences the past, and as if consciousness plays a fundamental role in determining physical reality. These behaviors can be calculated with extraordinary precision, but they cannot be explained in terms of familiar concepts. The mystery persists because it might be intrinsic to the nature of existence itself. Some aspects of reality might be beyond conceptual understanding, not because of limitations in human knowledge, but because conceptual understanding itself represents a limited approach to engaging with the deeper structures of the universe that govern physical processes. Mathematics might provide access to truths that cannot be expressed in ordinary language or visualized using familiar conceptual frameworks. This suggests that the ultimate nature of light and of reality itself might always remain partially mysterious. The universe might be designed in ways that preserve essential mysteries while revealing enough structure to support the existence of conscious observers capable of appreciating both the revealed structure and the preserved mystery that defines the deepest nature of existence. From this perspective, the fact that we can calculate the behavior of light without fully understanding it represents not a failure of science, but one of its greatest achievements. Science has learned to work with profound mysteries rather than simply trying to eliminate them. It has developed mathematical tools that can engage productively with aspects of reality that resist conceptual explanation. The light that surrounds you carries these mysteries. Every reflection, every shadow, every color represents processes that transcend ordinary understanding while remaining mathematically accessible. Feynman's legacy lies not in solving these mysteries, but in revealing their depth and beauty, and in developing tools that allow us to engage with them productively despite their ultimate and complete inscrutability. The universe keeps its deepest secrets while sharing enough of its structure to make science possible. The light that Feynman studied so carefully continues to behave in ways that no one can fully explain or understand, reminding us that reality itself might be far more mysterious and fundamentally wonderful than we ever could imagine it. B.